Yes.
When we release solutions for the assignments, do you think we should like briefly ask if people have questions about them, or is that unnecessary?
We should ask what questions? What questions?
Like, if anyone has wants to explain like a homework question or two briefly.
Oh, whether they have any questions for the solutions. I mean,
yeah,
they're always free to ask, but yeah, why not? Doesn't hurt. If they want to have, like, I don't know, what are you thinking about having some session where solutions are explained, or?
No, just like I remember in the bandits class, like every now and then, maybe if there was like a hard homework question, we'd like briefly go over it if people got stuck on one.
Oh yeah. Oh, okay. I see. All right. That kind of makes sense. Like, I think that we can do this on Slack now, and then if there is a need, then we can do that real time or something, rather than sometimes the explanations through Slack are just painful because, I don't know, I misunderstand what other people say, they misunderstand what I say, like it's just a mess. Written communication can be very difficult, but some of the times, like, yeah, like if it's an easy to clarify thing, then sure, it can be answered in Slack. All right, shall we get started? I think we should. We have quite a bit of things to do today. All right, do we have any other admin things to talk about beforehand? I know that some people wanted to have the submission deadline extended for the first assignment because this time is largely overlapping with the deadline for ICML and COLT, and people may be busy, but I say that let's discuss this on Slack. If someone can start a thread there, and then we can see whether maybe it should just be a quick poll on Slack or just a quick question, or I guess maybe a poll of like, is there anyone who opposes this, blah, 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 and then if no one opposes it, then like I'm open to this. Eventually we'll need to catch up, that's all. Just because the first deadline would be, I don't know, like postponed by, let's say, a week, doesn't mean that the other deadlines will also get pushed back, because then we'll run out of time. All right. Other than that, I think should be good to go. Website lectures are going to come soon. The other's been released. Thanks for all the feedback on Slack. Catching all the little bugs. Keep them coming. So with that, today I'd like to talk about two things. I want to go back, actually, because it's pretty important, this topic. And I want to discuss policy iteration a little bit more. So very briefly, we discussed what policy iteration is, the results available for policy iteration, but we didn't prove the results. I just alluded to how you prove them. And I think it would be good to prove these results. So I will spend some time on proving them. And the other topic is moving on. And I'm going to introduce what's called local planning. Or online planning as a way of freeing ourselves from the need to specify an action for every state in the environment, because there could be just too many states. So in local planning, the planner will be able to interact with a simulator of the environment, and it only needs to come up with an action at an input state. And it can do all these interactions, computations, then it has to spit out an action. So that's the other topic. I don't know how far we are going to get there, but that's the next big topic. As a way of moving towards planning algorithms that are more useful if the number of states is so large as typical that the tables that would describe, policies or whatnot, wouldn't even fit the memory, right? You can just do this local planning thing. All right. So with that, let's start with policy iteration. So as usual, we have an MDP. This policy iteration. We have an MDP. Okay. We have a state space, an action space, transitions, rewards, discount factor. And in policy iteration, as I explained in the last lecture, you start with a P0 policy, which is a memoryless policy, and then you produce P1, and then P2, and so on and so forth. And the rule for doing this is that P of k plus 1 is greedy with respect to the value function of the previous policy, of the last policy that was obtained in this sequence. And what this means with our operator notation is that if you take the policy evaluation operator underlying T of P k plus 1, the policy evaluation operator underlying P of k plus 1, and apply it to this value function, then that gives you the same result as if you apply the bare optimality operator. Just calculating one step look ahead and greedy actions, and then that determines this policy. So if you want to write it out, that pk plus 1 assigns to a state S. If you have a deterministic policy, then we are not going to spend time on describing the whole distribution, which has zeros everywhere, the whole distribution of reactions that has zeros everywhere, except at the action that is chosen by the policy. But rather, we're going to take the liberty and just treat the policy as a map from states to actions. It's a deterministic policy. And here, you can choose any maximizing action of the one step and one look ahead with respect to this value function that you obtained. And you just repeat this. So step 1 is to get a value function, and step 2 is to update the policy by this rule that's written here. So this means for every state you have to compute this these BAML lookouts for every action, and then choose an action that is maximizing resolving the ties, let's say in a systematic manner. So the systematic resolution of ties only helps you to decide that we're done, like we arrived at the optimal policy. So this is tie. All right, so this is a fine procedure. The first thing to know about it is that it's at least as fast as value iteration. And in particular, because of this, it holds that if you take the case policy that is computed and you compare this to the optimal value function, the distance measured in this max norm is going to decay exponentially fast. So you take the distance that you would get at the beginning, and there is a discount factor. We call that this is between 0 and 1. So altogether, this is an exponentially decaying sequence, rapid convergence, but it's not faster than value iteration. And the proof that proves that this holds is based on comparing the progress to value iteration. So the proof is based on this idea that what happens is that V star is an upper bound on any of the V of pi of k, which will be upper bounded by T of k, T applied, the Bellman optimality operator applied k times on the value function of the very first policy. So we claim that this is going to hold. Well, this part is obvious because the optimal value function is an upper bound on the value function of any policy. So this is the questionable part. But before we prove this, just notice that if this holds from this result, the claim of the lemma immediately follows because T is a contraction. So this guy converges to V of star at this geometric rate, right? So we know that if we calculate the distance between these guys, we increase the distance if we calculate it with respect to the value iteration distance. And then I can plug in T raised to the power of k over there, because V star is the fixed point of the Bellman optimality operator. And then apply that T, the Bellman optimality operator is a gamma contraction, you get the desired result. Right? So indeed, proving this outstanding question mark thing, this thing is going to be sufficient to show that the lemma holds. Sorry, proving this is going to be sufficient because we already know this. So we only need to prove that V of pi of k is greater than equal to T of k of V of pi of 0. So this is what we need. And we're gonna do this by studying what happens in a single update. So in a single update, what happens is that, so let's say we're going from k minus 1 to k. Then what we know is that T of pi of k applied to v of pi k minus 1 is equal to t applied to v of pi k minus 1, right? So because pi of k is greedy, so that's just the definition of the process. And we also know that this guy is at least as large as t of pi k minus 1 applied to v of p of k minus 1, the value function of the k minus 1's policy and its Bamel operator, because this has a max in it, and this just like chooses the actions based on some arbitrary thing like pi of k minus 1. And we chose this so that this is equal to v of, that this is just a value function, because the value function is always the fixed point of the underlying Bamel operator. So we see that this sequence of inequalities holds. So the usual thing is to apply T of the Bamel evaluation operator on both sides. So let's see what happens then if I apply it on both sides. All right, I get this inequality because T of pi k is monotone as an operator. And now notice that we have this equality here. So T of pi k applied to V of P of, like the value function of the k minus 1's policy, is the same as T applied to V of P of k minus 1, which is of course again bigger than equal to the value function of the k minus 1's policy. So I can keep doing this, right? Like I can apply again the Bamel evaluation operator of this case policy, and then I will get, if I do this any number of times, let's say I times. So formally you would say that, oh, by induction on I, then you can prove that this holds. Right? And now, if you let I go to infinity, then the left-hand side converges to the value function of the new policy. Right? So we got that the value function after an update, the value function of a new policy is at least as large as the Bamel optimality operator applied to the value function of the previous policy. Right? So this is greater than equal to this. Since this can also be applied to the value function of the previous policy, that introduces another Bamel optimality operator in the value function of the previous one. And you can unroll this back up to the very first one, and you get this inequality, right? So the proof is complete. So this is greater than equal to t squared of v of pi k minus 2, and so on and so forth. The exponent and this defect in the index are summing to are the same, right? And so the exponent gets k, then this defect becomes k, and we arrive at this inequality. So we get pi naught there. So we're done. Okay. Good. All right. Next page. That was very quick. I didn't want to click there. Do you have any questions? So this is based on this comparison argument to value iterations. So this basically shows that policy iteration has to go at least as fast as value iteration. Doesn't quite show whether it's going faster, but it shows that it goes as fast as value iteration. And in particular, you have this geometric decay of the error, which is the subject of this now. Let's call it lemma 1. Right? Okay. To get the result that I want to show, I need something else, which is interesting and valuable on its own, even though it is a very, very simple one-line identity. And I like to call this the value difference identity. And this will lead to something that's called a performance difference lemma that you may have heard about. So the value difference identity says that take two memoryless policies, pi, pi prime. These are memoryless policies. We care about comparing their value functions. It generally seems to be useful to do this. Let's say, I don't know which way I want to compare them. Maybe this way. All right. So what do we know about the value function of, let's say, v of pi prime? Well, recall that v of pi prime was the fixed point of the evaluation operator of this policy. So this means that this is equal to r of pi prime plus gamma, the transition matrix that results from using this memoryless policy pi prime in the MDP, and applied to this value function. And if you reorder this, then you can express v of pi prime from this equation. This is a linear equation, and you get that v of pi prime is just the identity matrix minus gamma times p of pi prime inverse applied to the reward. The reward vector that you incur that gives you the rewards, the immediate expected rewards that you incur in every state by following policy pi prime, right? So they're just reordering this. And okay, so I just want to pull this out, so I have to pre-multiply with the same matrix here so that nothing changes, right? So this cancels this. So the second term is replicated. The first term is replicated based on this identity. It should all be good. And now observe what happens here. So you can group this term with these terms, right? So there is minus minus, so that's a plus. So that just means that there, what appears in the bracket is the Bellman operator underlying policy pi prime applied to v of pi, right? So the underlying terms correspond to this, and we have to still subtract the value function of policy pi because that corresponds to this identity multiplying that value function. Okay, so this is just algebra. Because this appears a lot of times, I'm going to give it a name. I'm going to call this the G of pi prime and pi. And this is the advantage vector or whatnot of pi prime relative to pi. But this is just like, we have to give it a name. Don't overthink what this means. I mean, like, it's just like, you know, if I apply t of pi to v of pi, I get back t of pi, v of pi. So instead of t of pi, I can apply some other operator, the operator of some other policy, t of pi prime, and I can look at the results statewise, compare the results. Do I see a gain? Do I see a loss statewise? If the new policy would be greedy, whatnot, or like at least better, then this would be non-negative at that state, if it's a sort of better policy. So in some way, this is indeed the advantage of pi prime relative to pi. It's like just like a one-step comparison. And so with this, we can write this identity as saying that for any pi prime and pi memoryless policies, the value differences can be written as the identity minus gamma times transition matrix underlying pi prime inverse applied to the advantage of pi prime relative to pi. So now note that if pi is equal to pi star, an optimal policy, an optimal memoryless policy, then no policy has any advantage to pi star, then G of pi star, so sorry, G of pi prime, pi star is going to be less than equal to 0. So here 0 means the all 0 vector. So statewise, you can't improve upon an optimal policy. None of these things are unique in general. And you can also reverse this. You can say that if there is no way to improve upon a policy with this, then that policy must be optimal. That's a homework. So this is a characterization that for every pi prime memoryless policy, G of pi prime, pi star is less than equal to 0. This is a characterization of optimality then. I mean, this holds if and only if pi star is an optimal policy. So this kind of tells us that maybe a good way to measure progress in whatever algorithm is to use the negative of pi and pi star, pi of k or whatnot. Like if you have something like policy iteration or any other algorithm that comes up with a sequence of policies, maybe this is a good way of measuring progress. If you take any state and then you just like would look at this negative advantages with respect to pi prime, so the disadvantages, then you would start maybe with a big value and then you're decreasing towards 0, right? Like Ideally, that's what you expect to happen. So here is your negative g of pi naught, pi star. And then ideally, after some number of steps, your negative advantage or disadvantage is going to be small. So this is what we are going to set off of proving, all right? To make this precise, so in policy iteration, what happens is that this decrease happens in the max norm, and it's geometric, at the geometric rate, okay? And this will result in the following lemma. No matter how you take an initial policy, such that this is not an optimal policy, because then there is nothing to be proven about policy iteration. If you are lucky enough to start with the optimal policy, you are done. There exists some state such that for all iteration numbers larger than some function of gamma, and it happens that this is just like the effective horizon, the policy that policy iteration produces at state S naught is not going to choose the same action as pi naught, and actually we know that this action is not optimal. So it's okay not to choose it. We will never ever choose it again, and since policy iteration converges, this action cannot be optimal. All right, so this is what we want to prove. And for this, we start with this idea of measuring the progress.
Chava, before that, can you take a question?
Oh yeah. Look at
the chat.
So Yunfeng said, I'm confused why pi and pi prime share the same. They don't share. No, there is no typo, and they don't share anything. So I guess the question was related to the value difference identity. And in this value difference identity, I only expanded the value function of pi prime. I didn't do anything with the value function of pi. I just copied it. Of course, there is a symmetric identity, so you can reverse pi prime and pi, and like you get the symmetric identity, where you have I minus gamma pi. You can do that. I just don't need it, but you can do it. Does this answer the question?
I guess I have a question about how the first equation holds.
By first, you mean this one?
Yes.
Okay. So basically, I took this, I reordered it. So I said that V of pi prime is equal to identity minus gamma times P of pi prime inverse applied to R of pi prime. I plugged this in, and that's the only thing I did. except that here I started to introduce the bracket because I want to pull this out, right? So now this guy cancels this guy. That's a pi prime too. All right. So do we agree that this applied to this? That's v of pi prime. Do we agree that if you multiply this with just this whole guy, then you get v of pi?
Is that identity you've written at the top in pink follow from what we prove on the assignment? Assignment 1? Where you look at the geometric series, gamma.
Yeah. I mean, like this is just the fixed point equation. So if we know that v of pi prime is the fixed point of its underlying policy evaluation operator, and I just wrote out what the policy evaluation operator does, right, in detail with this vector matrix notation. I'm just using the vector matrix notation to my advantage. Right. Good. Right. Okay, so back to the proof. All right, so we want to prove that the negative advantage of pi of k compared to pi star is somehow small. So we start with this identity that we have here, right? Like, where is this identity? This identity. And so I'm going to have, this is going to be pi star, and this is going to be pi of k here. Okay? And I have a negative sign, so just have to be careful. Oh, sorry. So pi prime is pi of k. So this goes to the other side. And then I have, we have pi star. Oh, that's just, okay, pi star's value function is v star. So let me just write v star. So here, by the way, pi k is what is produced by policy iteration, if that was not clear. So we're going to use that later. And right. So far we got this. All right. And so this is, if I multiply with the identity, I just get v star minus v of pi of k minus gamma p of pi of k times v star minus v of pi of k. All right. So I just expanded that multiplication. And now notice that this is non-negative. This is a stochastic matrix. So this, as a vector, is non-negative. And I'm subtracting a non-negative vector. Okay? Then I get something bigger if I don't subtract anything. So let's just do that. So this is the bold step to drop some term just like that, right? And so now we had this lemma. I want to bring in g of pi naught and pi star. And so the previous lemma allows me to compare the value function difference to the optimal value function of the case policy to the same with the zeros policy. So I'm going to use lemma 1 here. So take the absolute value of both sides. You still get the inequality. The negative sign is going to be gone. Take the maximum over all states. You get the max norm. So in other words, if you take the max norm, you still get the inequality. So we get that G pi of k pi star in max norm less than equal to v star minus v of pi of k, the max norm. And now use the lemma. Right? I need to turn the page. So let me just copy this. Right? Just use the lemma that policy iteration converges exponentially fast. And then now I want to bring in the advantage or disadvantage of pi naught relative to pi star. So recall the value difference identity. This is going to be pi naught now, and this is pi star. Okay. So since we have this identity, I can write that this previous thing is equal to gamma to the power of k infinity norm applied to this inverse matrix and now in homework 0 you learn about the induced norms for matrices, and they are defined in such a way that you can pull out the matrix norm, the induced matrix norm of a matrix from a matrix vector multiplication always. And all this contraction business, I mean, you can do the von Neumann expansion for this. So this is the same as sum of gamma I pi p of pi naught to the power of I, and then bring in the norm, triangle inequality applied, and use that and induced norm for matrices is submultiplicative, and use that the max norm of a stochastic matrix is 1 to get that this, the induced norm of this, is smaller than the sum of this geometric series, which is 1 over 1 minus gamma. They're actually equal. But we only need that. They're less than equal. So with this, I can replace the first term with just 1 over 1 minus gamma. That was easy in retrospect. And then I have this progress term. Okay.
Chaba, does submultiplicativity hold for max norm?
Well, it's for the induced matrix norm. And in homework 0, I think everyone proved that for whatever induced norm you have, submultiplicativity is going to hold. It's a property of induced norms. And this is the induced norm by the max norm. If you use the matrix as mapping vectors to vectors, and with respect to the max norm, you define the induced norm. So both norms, like the input norm is in the max norm, the output norm is the max norm. You calculate the induced norm for the matrix. Well, that's the norm that I'm talking about here. And every induced norm is submultiplicative. So that's a general property. It's or maybe it's an exercise in the new homework. I don't know. I forgot. Was it an exercise in homework 0?
Yeah.
I think it was, right. Okay. Yeah. So this is general property of induced norms. Okay. So we have this. Yes.
Yeah, I just had a question. Before the last step, what did you call it? The von Neumann expansion?
Oh, von Neumann expansion. Yeah. So that's also was on homework 0. So if you have I minus A, identity minus matrix A, and you want to invert this, if you are lucky and the inverse exists, then it should take this form. This is called the von Neumann expansion. And this looks really fancy until you try it with numbers. So if A is just a real number, so then what the heck? Like, this is just 1 over 1 minus A. And this is just the geometric series. So this takes a very familiar form for not matrices, but it happens to work for matrices, happens to work even for bigger things, these operators that act on infinite dimensional spaces. As long as these operators or norms are nice, their spectral radius is less than 1, which holds for the stochastic operators.
Okay, thank you.
Yeah, good?
Yeah.
Yeah. This is also like, you go back to homework 0. It will make, like, that homework will make more sense after today's lecture of like, why do I insist on these things? Yeah. All right. Okay, so we arrived at this. Okay, look at this. The progress is geometric decaying. That's great. But from this, we should somehow extract like a really definite result that we set out, which is that there is this state where pi naught is choosing something suboptimal, and after such and such many iterations, that suboptimal action is never going to be chosen again by policy iterations. You can cross it out. So this is the progress that we are making. So this is a progress lemma. I like to call it like that. So how do we extract this? Well, initially, so if this was 0, then you know that pi naught is optimal. So this is going to be strictly less than 0 at some state. So we can pick the state that the negative advantage of pi naught with respect to pi star is the maximum amongst all those advantages or negative advantages. It doesn't matter. This is positive because pi naught is not optimal. So let's pick this state. I claim that this is going to suit the bill. Right? So let's see what's happening here. So we have this previous inequality, and on one hand, here on the right-hand side, we have gamma to the power of k, 1 minus gamma, and I can plug in the negative of pi naught, pi star, disadvantage, at S naught, because that's the definition of S naught. Okay? So I can write, I don't know, gamma to the power of 1 minus k, 1 minus gamma is negative pi naught, pi star, S naught is greater than equal to this infinite norm. And since we need to show this property relative to state S naught, well, I propose that we just say that we just, like, instead of the max norm, which can take a large value, we just take one value, which is at S naught. That's less than equal. And I have to negate that because all of these values are non-negative. And, first you have to take the absolute value, and then you take the max, and taking the absolute value is the same as taking the negative of the negative values. We know that all values are not positive, at least. So, yeah. Right. And okay, so what does this mean? What are these advantages, disadvantages? So what's the definition of this G? So it's time to plug that in back. So the definition of G pi prime, so the advantage of pi prime relative to pi, it's just this difference. So let's plug that in. So gamma to the power of 1 minus gamma. And I pull out the negative here. This is Okay, I put back the negative, and I flip these guys. Look, I just do this. Oh, and this is at S naught, right? So take all this at S naught. Is greater than equal to, and now I just have to do the same thing with pi k. I like to write it this way. It's better this way. I'm going to flip the other one too. So let me just flip this. Right. So let's check. So V star is of course at least as large as any policy evaluation operator applied to V star, because you know, policies can only lose compared to optimal. So these are all non-negative. So this is kind of like how much pi naught loses compared to optimality in some measure at state S naught. And as you iterate, eventually, so this is a, at S naught, this is a positive number. As you iterate, once gamma k one minus gamma becomes less than 1, right? So if k is large enough, then this happens. Then you can further upper bound the left-hand side by the difference between V star and T pi naught applied to V star at S naught. So basically dropping this other guy, right? So when this happens, then we see that this disadvantage of pi naught is strictly reduced. Right? Okay. So I just like put that, you know, like this is strictly less than 1, and then copy the whole same thing, right? And then read out what's on the left-hand side, what's on the right-hand side. And I wrote that here. And we have a strict inequality here. That's the key, right? So just need to choose k large enough as a function of gamma such that this holds. Because then I can upper bound gamma to the power of k or 1 minus gamma by 1. Okay? So what does this mean? It just means that if k is bigger than this k star of gamma, then T of pi k applied to V star at S naught is going to be strictly larger than if we do the one-step BAM on look ahead after under pi naught and look at what happens at S naught. Look, I just copied this inequality and like moved the this to the left-hand side, or multiplied by -1, that's the inequality, and cancel the v star, right? So that's just algebra. And so what does this mean? Well, it means that if you want to write it in details, you can write it in details. This is what it means. It means that whatever pi naught was doing at S0, it is not possible that pi of k is doing the same thing, because you get a strictly bigger value. If it chose the same action, it should get the same value. It cannot choose the same action. It has to choose some other action, right? So if pi k was choosing the same action as pi naught, then we would get the same value. We're just talking about what happens at S naught. So that cannot happen because we know that these inequality is strict, it holds. There's this strict inequality holds. So pi k at S naught just cannot be the same as pi naught at S naught. If you write out like this individual thing, it depends on what pi k chooses. You cannot choose the same. It actually should write it this way. You have deterministic policies, then this is what happens. You can just plug in what the policy chooses in the place of the actions. That's the one-step Bellman look ahead. And so we see that the same choice cannot happen, because otherwise this strict inequality wouldn't hold. Right? That's the magic. So we're done. So we just have to calculate what k star is. So what is k star gamma? So that's the smallest value of k such that this is smaller than 1. Well, we already gave that the name of the effective horizon at the precision of 1. And that was log 1 minus gamma divided by log 1 over gamma. If you saw this inequality, then this is the critical value. So this is the value of k star. Which is roughly, if you don't care about the logs, then this is just 1 over 1 minus gamma. Right, so we talked about that this is actually bigger than this, right? So if you demand that k star is bigger than this, then of course it's bigger than this, then this holds. And so up to log factor, after 1 over 1 minus gamma steps, policy iteration will eliminate at least one suboptimal action. And now we can get back to the table that I was drawing the other day. You can have the states here, and you can have the actions there. And then you have all these A actions, and then you have all these S states. And every K star iteration you have one cross appearing in this table. And then another cross appearing in the table after K star more iterations. Because policy iteration decided not to choose that action ever again. You can keep applying the lemma, this last lemma, this progress lemma. to the policy that was obtained after k-star iterations, and then the policy applied, and then the MO applied to the policy obtained after 2 k-star iterations, and so forth. Okay? And each time you do it, the previous progress lemma still holds. So the previous cross is still there. It's staying there. It's monotonically getting rid of suboptimal actions. And how many times can I do this? Well, roughly S times 8 times. But actually, like, every row has to have one optimal action, so it's SA minus A. If you have this more general situation where you have varying number of actions in each state, then this would be just like the total number of state action pairs. So if you don't have this rectangular situation, then that's just like the total number of state action pairs minus the number of actions. So from this, it follows that if k is bigger than SA minus A divided by 1 minus gamma log 1 over 1 minus gamma. And actually, I don't have to put in O there. I guess, okay, I put an O there because here we would need to take the seal of this number, so I don't want to deal with that. Just like +1. So if k is this big, then pi k is optimal. All right. That's cool. So this proof is due to Bruno Scherer, who is in France, and other people who worked on this include Yin. He was kind of the first one to figure out that something like this should hold. But he had a higher order polynomial and a much more complex proof. And there's another guy, his name is something Hansen. He also simplified the proof of Yin, and then Bruno simplified it further. And then here we come. We have a very nice, beautiful short proof. Okay. Any questions? Shouldn't it be minus S, not A, since we need each state to have an optimal? Oh yeah, that's absolutely correct. I don't know why I write that. Yeah. Good catch.
I had a quick question on the previous page. If you could go. Yeah, so where did the V star minus T pi 0 V star come from?
Which?
On the right-hand side at the bottom.
Right-hand side on the bottom. I wish I had a pointer in this thing. Here? This one?
It's like 2 lines above.
Here?
Yeah.
Here?
Yeah.
Well, this was just this guy.
Okay.
Just expanded that.
Okay.
I was just rewriting this, expanding the definition of G.
Okay.
So G was just a shorthand for this differences. Okay.
Okay. Thanks.
Anything else?
I also had a question. So this is a pretty recent proof, right? So why weren't people able to do this before? Was there's something new introduced in the proof technique, or maybe
I mean,
people just
Ye's proof didn't look anything similar to this. But after seeing his proof, other people who were familiar with proof techniques like the one presented today were like, there is no way we cannot simplify this proof and just like have a very simple proof with the existing techniques. If you look back at the proof, like pretty much all the steps in it were used in other proofs at one stage or another in proving various other things. So people kind of knew about this like a long time ago. And it's just like these little steps that you need to drop this. You have to be brave enough to take the max norm over there. And like this order of like things doing this, that the progress should really be measured with respect to these advantages. That comes from Ye, which in retrospect is something we should have tried, but it's a good lesson in that, policy iteration was proposed by Howard in the 50s. There is absolutely no reason this proof couldn't have been done in the 50s. Yeah. There is nothing in it that people at the time didn't know. They knew everything. Yeah. It's fascinating. It's good to be a graduate student at this time because there's still a lot of these low-hanging fruits which are like really simple and nice and crucial results. So the one presented today is from Bruno's paper as that appeared on the internet in 2013. And it appeared in a journal in essentially identical form in Mathematics of Operations Research in 2016. All right. Okay, so we don't have much time left, but I still want to spend some time on this local planning idea because it's also very cool. Or at least I introduced the framework. I have 10 minutes. So let's do this local planning. So the problem that we came across is that if you require that the output of the computation be a big table, then if the table needs to be big, then it's just too bad. So what's second best? It would be just to say that, well, you have, let's say, this simulator that you can interact with that takes states and actions, and it outputs next states sampled from the underlying transition dynamics, and it also outputs the corresponding reward. And like here, I'm again assuming that it's just deterministic reward without much loss of generality. And if you have a simulator like this, then you could set out to solve the following task. Your input is going to be some state. And then here with the simulator, we only assume that, like you can remember the states that were given back to you, and then you can reset the simulator to any of the states you have ever encountered in this process, including S0. So at the beginning, you're given S0. So there is this big MDP with this big state space. Here is the big state space. You start with S0. And you can, try different things. You get to other states. You can try other things from there. And so on and so forth. You can have a local view of how the MDP looks like. Okay. And so we're not going to demand that at the end of this computation, you should come up with a policy which assigns some action to every state, because there could be just too many states. We just demand that you output an action which, after some computation interaction with the simulator, so you output an action. And of course, this action is going to be random in general, because even the simulator is returning random next states, right? So in general, this is a stochastic action. And the algorithm that you use, you can use it in any state. And you can look at the distribution of these actions. So the idea would be that you're at some state S0, you apply this planner. So this is the local planner. And then you look at like, okay, now I apply A, and I make a real transition in the real world. And I assume that the real world matches my simulator. And now my new state is here. And I can start calling the planner again, right? So this is the new S0. And I can repeat this. So this way, the planner is encoding a policy, right? And if between calls, the planner doesn't remember what it learned about the MDP, so it just like reset the whole program, start again. You do whatever computation you need to do. You don't remember about like what was going on previously. Then you will have a memoryless policy. So in effect, you can think about that the planner is implementing a memoryless policy. So you can ask, like, what's the probability that A takes the value of A? And like this only applies if the input to the planner, so this depends on the planner. So if the input to the planner was S0, and then you call this the probability under this policy pi. So if you collect all of these probabilities, they define a stochastic memoryless policy. And if you keep calling the planner in an online fashion, so sometimes this is also called online planning, right? So imagine that you are interacting with the real world now, and you're at some state, but you have a simulator that faithfully describes what the world is. You close out the simulator, do your search, do your computation. You come up with an action, you execute the action. In the real world, the state moves. So that corresponds to executing this policy. And so here we are making the big leap of faith that the real world is the same as the simulator, but that's a start, right? Like you should start somewhere. If you can't do anything in that situation, then we won't be able to do anything anyways. So not caring about that, there could be a possibility that the simulator is not the same as the real world. We're demanding that the planner should be such that the policy that it implicitly defines is a good policy if you execute it, right? So altogether, what this means is that we demand that the planner should output a policy pi this way, such that this is delta optimal. But delta is also an input to the planner. So let's imagine something really simple here. Okay, so let's imagine that you have a deterministic MDP. So if you have a deterministic MDP, and you need to come up with a good way of acting, you can just build this look-ahead tree, right? You start at some state, S0, and you have, let's say, 2 actions to try. So keep it even simpler. Doesn't matter how many actions you have. You would have an A-array tree. If you try both actions, you get some resulting state. For action 1, you get some state. For action 2, you also get some state. You can keep doing this. You can build this full binary tree. And let's say you stop at depth H. And when you're getting back the next state, you also get back the reward, right? Like you will get R of 1 as not here. You have R of 2 as not here. So you can record the rewards along each of these transitions. So if you need to calculate how to act, well, we already know that since there is discounting, what happens after the effective horizon, this 1 minus gamma, I don't know, delta, is not going to influence. It only influences the outcomes up to an accuracy of data. You can only use data if you're not looking further ahead than the effective horizon. So you can build this tree, and then you can start to calculate the values as if this was full MDP. So in the bottom of the tree, you have a state, you have 2 actions, and that's the end. And you can say that, well, the reward here was 1, the reward here was 2. So what's the value of this guy? The value of this should be the maximum of 2, so it will be 2. So there is also this state, which was also at the very end. Like you first calculate the values for everything in the very last layer of this layer tree. So at level H minus 1. So here you see, I don't know, like a 1 and a 0. Then the value of here should be 1, right? Like that's the total reward to go. And now if there is an action that's connecting these 2 guys, so let's say you're done with the value calculations for the very last layer, you go back to the previous layer and you say that, okay, I have an immediate reward of 0 here and the 1 there. So what's my total reward? Well, I should start discounting, right? So here on this path, it's going to be 0 plus gamma times 2. So altogether it's gamma 2. And here it's a 1 plus gamma times 1. So here it's 1 plus gamma. And then I can compare the gamma 2 and the 1 plus gamma and take the maximum of that and assign that here. You do this calculation backwards. It effectively emulates value iteration. It's just that you have this finite horizon cut because nothing matters beyond the planning horizon. And at the end of the day, you calculate some value here for action 1, some value there for action 2. Like, I mean, like for the underlying states, you calculate their total discounted return in this recursive fashion. And then when it comes to make a decision here, just sum up the immediate reward, discount the values of the underlying 2 individual states, compare whichever action wins, choose that. This procedure for deterministic environments, okay, it is going to be a little bit expensive if the effective horizon is large, right? Because we're going to have some, I don't know, a to the power of h in general. This is an A array tree. We're going to have a to the power of h leaf nodes and nodes roughly altogether, that many in this tree. And that's the amount of calculation that we need to do. That's the amount of simulator calls that we need to know. So that's basically the complexity of this whole process. But notice that the number of states didn't matter. Like, there is absolutely no appearance of the number of states here. So we were able to get away with a complexity, query complexity and computational complexity, memory complexity, everything that is independent of the number of states. So that's a really cool thing. Independent of the size of the state space. Could be infinite, like it doesn't matter. But the story here, in a nutshell, is because of discounting, it is not worthwhile to look far ahead into the future. If you have a deterministic system, then this means that you just like build this look-ahead tree of finite lengths, finite depths, and you're done. You don't need to do anything else. And unsurprisingly, the number of states, like how many states altogether there are in the environment, don't matter, because you can just cut the search after a certain depth. All right? So the question for us that we will try to answer next time is whether this extends to the stochastic case. Are stochastic MDPs much harder in this respect? How much? Does it depend on the amount of stochasticity, somehow the structure of the MDP, and so on and so forth? Or can we get away with some amount of queries and calculation that, okay, it's too bad this is exponential in age, but it's still independent of the number of states. And previously we had this lower bound that said that, well, if you demand that you output, you know, like an optimal action at every state or a near optimal action at every state, well, of course, then you have to at least enumerate all the states. So the calculation has to scale with the size of the state space. So that's the difference between this local view and the global view, or the online planning and the global planning. In global planning, if you require that like the output is working everywhere, so that means that you have to do all the calculations, all the access to the model, and then you cannot have access to the model anytime later, and you have to just like produce an output which is good everywhere. That's hard. In general, that's really hard. Then you shouldn't be surprised if the complexity scales with the number of states. But if you allow yourself this local planning, it should make sense, right? So you build a simulator, like you maybe build a model, and then just want to call the planner. Whenever you need some action, you call the planner. So what action should it give to you? Well, it should give you an action such that if you keep following the planner, so that's like the result in this value function. And this gives you high values. All right. So that's kind of the story that we are going to further in the next lecture. And so one last question maybe from the chat. The question is from Erfan. Do we have access to the transition probability distribution in the stochastic case? You say like if you have a lot of states and you would want to read this probability vector, then that would be too bad. Because then the time you need to spend on this is going to be proportional to the number of states. It's too much. So rather than this, what we're going to assume is that somehow the simulator can give you a random next state from this distribution. So that allows you to get away from this requirement that you would need to read a long vector just to know what's going to happen with the next states. And the question is, does this save you? Very good question.
For these MDP trees, do people consider the case where is it more interesting to consider the case where the reward has some structure? Because I can come up with an MDP where the reward is 0 everywhere and then 1 for one transition, but maybe that's not an interesting problem because that's just a needle in a haystack.
I mean, before we consider further structure, we should investigate the simplest case, but yeah, there are all kind of possibilities of how you can further reduce the space of MDPs that you're considering. I'm not really aware of any work that would, reason with the rewards. I think that you just want to keep the rewards general, but later on we'll spend a lot of time on putting other regularity assumptions on the MDPs. That will, address some of the. So this is still exponential in the effective horizon, already in a deterministic problem. That should bother us. And the needle in a haystack example shows that you can't do better than that, even for deterministic. That's like homework 0, right? Like that was the needle in a haystack problems. And like no algorithm can find the needle in a haystack in time less than, sorting through everything divided by 2. Like that's the max that you can do, right? It's nothing. So, yeah. All right. Thanks.
Thanks.